Hello everyone, this is Pawan Inania, Assistant Professor in the Department of Electronics and Communication, Government Women Engineering College, Ajmer. I welcome you all in this lecture series of signals and systems. In the previous lectures, we discussed about the basic jet transform and explained that how can we calculate the jet transform of any discrete time sequence. Then we discussed the properties of jet transform and the importance of that properties. Today, we are starting with a very important topic, inverse jet transform, in which we will recover the discrete time sequence from a frequency domain signal. So let's start with a basic relationship between the discrete time Fourier transform and the jet transform. This is the basic relationship between the discrete time Fourier transform and the jet transform. X r e to the power j omega. When we put z equal to r e to the power j omega, then we have this type of relationship. This is the discrete time Fourier transform of x of n multiplied by r to the power minus n. In the inverse Z transform, we can convert or recover the basic signal x of n, which is the discrete time signal. For inverse Z transform, we can obtain by partial fraction expansion, power series expansion and contour integration. These are the particular methods which is very useful to calculate the inverse Z transform. So we can understand this inverse Z transform by taking some examples. First of all, we have the first example, x of z is equal to 1 upon 1 minus a z inverse, and ROC is given to you like mod of z greater than mod of a. This z greater than a means this signal is right sided and the ROC is the outer side of the particular circle. When a is greater than 1, then we can see the ROC like this. Okay, so a may be greater than 1 and a may be less than 1. So we have discussed this Z transform in the previous lecture, that L to the power n u n having the Z transform 1 upon 1 minus a z inverse, then the inverse Z transform of this 1 upon 1 minus a z inverse will be a to the power n u of n. U of n is associated with a to the power n because ROC is greater than or right sided. Okay. This is the second example where x of z is equal to the same function is given to you, that 1 upon 1 minus a z inverse, but ROC is different in this case. ROC is less than that particular a. So this is the left sided and ROC is inside this circle. So when ROC is inside the circle, then signal is represented as a to the power n u of minus n minus 1 because ROC is less than or left hand sided. Third example is, this is very important example in which we will discuss about some cases. X of z is given like this and we have to determine the z transform of this particular x of z. So the first case is ROC is greater than 1, second ROC is less than 0.5, third ROC is in between 0.5 and 1. Okay, there are two poles, first is 1 and second is 0.5. So we can have some steps for this example. The first step is to convert x of z to positive power of z. Okay, so this x of z is given in this question. We can convert this x of z in terms of positive power of z. So we will have z square upon z square minus 1.5z plus 0.5. X of z by z is equal to z upon z square minus 1.5z plus 0.5. We will use partial fraction expansion method to calculate the inverse Z transform. Mostly in inverse Z transform, in this topic, we will use the partial fraction expansion method. So the denominator is given like Z square minus 1.5 Z plus 0.5. Okay, and we can solve this expression like this. So after solving the expression, we will have Z minus 1, Z minus 0.5. Okay, so by putting this value in the denominator side, Z upon Z minus 1, Z minus 0.5. Okay, this is the step number 2. Partial fraction expansion will be used for this solution of inverse Z transform. So we can have the expression x of z upon z is equal to the constant a upon z minus 1 plus constant b upon z minus 0.5. So for partial fraction expansion, we can solve for this constant a. So after solving this constant a, you will have the value of a is equal to 2. You can solve by partial fraction expansion, and this method we have already discussed in the engineering mathematics. Constant b is minus 1. Okay, you can solve this a and b by using the partial fraction expansion. So finally, the constant a is equal to 2, constant b equal to minus 1. We can put the value of a and b in this expression. So x of z upon z is equal to 2 upon 2 minus 2 upon z minus 1 minus 1 upon z minus 0.5. You can multiply this z in the numerator side to z upon z minus 1 and z upon z minus 0.5. Okay. Then we can take this z outside the parenthesis. Z and z will be cancelled out. This z and z also will be cancelled out. Okay, finally we will have 2 upon 1 minus z inverse minus 1 upon 1 minus 0.5 z inverse. So there are two poles, z equal to 1, z equal to 1 and z equal to 0.5. Okay. So first case in which ROC is greater than 1. In this case, we can draw the ROC like this. The real part at x-axis, y-axis is the imaginary part. This is the unit circle for Z transform, and it's a first pole 0.5 and second pole is 1. This is 1 and 0.5, and ROC is given as the outer side of this unit circle. When ROC is greater than any pole, then we can say that it is a right-sided signal, and finally whatever the signal, whatever the discrete time signal, we will associate u of n with a particular value. So we have expression x of z equal to 2 upon 1 minus z inverse. So the Z transform of this 2 upon 1 minus z inverse, see here Z inverse is multiplied by 1. Okay, 2 upon 1 minus 1 Z inverse. Okay, so the Z transform of this particular part is 2. 2 is constant, multiply by 1 to the power n u of n because of the right sided signal, minus 1, this 1, multiply by this 0.5 to the power n u of n. So this is the final value of x of n when ROC is greater than 1. In the second case, when ROC is less than 0.5. Okay, so come to this point again. If ROC, there are two poles 0.5 and 1. If final ROC is greater than 1, then we know that ROC is always the common region for multiple poles. So there are two poles, and if final ROC is greater than 1, then the second ROC must be greater than 0.5. Then we can have the common region outside this circle. Okay. In the second case, when ROC is less than 0.5, then definitely the second ROC which is associated with this 1 must be less than 1. Then we can have the common region inside this circle. So if ROC is less than 0.5, then it must be less than 1 also. So finally, if both the ROCs are left sided, then common region is inside this 0.5, okay, and the final signal will be the left sided signal, and left sided signal is always defined by u of minus n minus 1. This is u of minus n minus 1 multiplied by this 1 to the power n, this is 1 to the power n, okay, and this is 1 to the power n multiplied by this numerator part 2, okay, and u of minus n minus 1, and second one is this 0.5 to the power n u of minus n minus 1. So it's a final result discrete time signal when the case is mod of z less than 0.5. Then we come to the third case, that is the ROC is in between 0.5 and 1. Okay, we can draw this ROC defined in this circle that the first pole is at 1, second pole is 8.5, and ROC is in between 0.5 and 1. Okay, we can see this ring as a ROC for this particular case. So one ROC is greater than 0.5, second is less than 1. So when ROC is greater than 0.5, then this signal will be the right sided signal, and when ROC is less than 1, then this signal will be the left sided signal. So for first part, this part is left sided because ROC is less than 1. This part is right sided because ROC is greater than 0.5. Okay, so we can define the final signal discrete time signal x of n sequence like 2, this 2 multiplied by 1 to the power n, 1 to the power n is always 1, and u of minus n minus 1 because the left sided ROC, minus 0.5 to the power n, this 0.5 to the power n, and u of n because this is the right sided ROC. Okay, so it was the example, very useful example for the inverse Z transform, in which we can recover any x of n sequence by the x of z. X of z will be given to you with a particular ROC, and according to that particular ROC we can define the time domain signal x of n like this. Now we come to the point, another very important point, that is stability and causality. So what is stability? The meaning of stability is bounded input produces bounded output. When we have any LTI system with impulse response h of n and any discrete time sequence is applied to that particular LTI system, then it will produce y of n, okay, which is the convolution of this h of n and this x of n. So for the condition of stability, the mod of h of n from minus infinite to infinite must be less than infinite. Okay, if impulse response is infinite for any type of LTI system, then whatever the x of n will be applied to that particular system, it will produce the infinite output, and we don't need for the infinite output, because output is infinite, then the value of that infinite is undefined. Okay, so the impulse response must be less than infinite. So if any x of n is given to h of n, which is having the value less than infinite, then final result is always uh, when h of n is finite and any signal is applied to that LTI system, then result will be finite. Okay. So the value of h of n should not be equal to infinite, because infinite is undefined value and we can't define that particular system for the infinite values. The stability of a discrete time LTI system is equivalent to its impulse response being absolutely summable. So this h of n must be absolutely summable. The second condition is an LTI system is stable if and only if the ROC of its system function h of z includes the unit circle, that is mod of z is equal to 1. When we discuss the Laplace transform, then for the stability condition, there was a particular case for which stability can be defined. What was the case? That there was x-axis which was the real axis and y-axis was the imaginary axis, and for the condition of stability the ROC must include the j omega axis. So in Laplace transform for continuous time signals and systems, there was a j omega axis, and equivalently in Z transform there is a unit circle. Unit circle means the radius of that particular circle is 1. So in the stability condition the ROC must include the unit circle. If ROC includes the unit circle, then it is a stable system. And second condition is h of n must be less than infinite. Second case is causality. A discrete time LTI system is causal if and only if the ROC of its system function is the exterior of a circle, including infinity. This is very important, including infinity. Okay, there must be no pole at infinite because ROC never include any pole. Okay, so for the condition of causality, h of n must be 0 for n less than 0. We can define this condition like this. This is the time axis and h of n is defined in only in this right sided part. Okay, h of n must be 0 when n less than 0, then it will be the causal system. For rational systems, if h of z is given to you, then ROC must be exterior of a circle outside the outermost pole. If there is multiple poles, then ROC must be exterior of a circle outside the outermost pole. Okay, ROC must be the outside of outermost pole. Then the system may be the causal system. Okay, the second condition is if h of z is given in the polynomial form, so there will be some numerator part and some denominator part. We can define this numerator part like a and the denominator part by b, then a must be less than b. A must be less than b means the order of this a must be less than b. Okay, order of a must be less than order of b. We can have some examples that h of z is equal to z cube minus 2z square plus z upon z square minus 1 by 4z plus 1 by 8. So we can see in this h of z that order of numerator is higher than the denominator. So no need to solve this is not a causal system because the order of numerator part is greater than the order of the denominator part. So it is not the causal system. We can directly define this system that this is the not causal system. Second example is h of z is equal to 1 upon 1 minus half z inverse plus 1 upon 1 minus 2 z inverse, and ROC is given as mod of z is greater than 2. Okay, in the first question there was ROC was not given in this question, but we don't need for the ROC because we can directly solve this question as the order is higher in the numerator part with compared to the denominator part. Okay, in this question we can't judge by seeing that what is the order of numerator and the denominator at first sight. So we are having some ROC condition here, z is greater than 2. So we can solve this expression like this, 2z inverse 2z square minus 5 by 2z upon z square minus 5 by 2 z plus 1. Okay, so we can see the order of numerator is equal to the order of denominator. Okay, z square here and z square in this side. So ROC, right to rightmost pole or exterior of a circle outside the outermost pole. So there is a pole 2, z is greater than 2, z is greater than 2. Okay, first pole is at 1 by 2, second pole is at 2. So 2 is greater than 1 by 2 and ROC is greater than 2. So ROC for this condition must be greater than 2 because the final ROC is greater than 2. Okay, so ROC must be greater than 1 by 2. Then we can say that the final ROC is greater than 2. Okay, because there is only 2 poles. So first condition is satisfied that ROC is exterior to outermost pole. Outermost pole is 2. Degree of numerator is not higher than denominator. There was a condition that numerator polynomial a, this is the degree of a, less than degree of b. It must not be greater than degree of b. This was the condition. There may be equal to a may be equal to b. Okay, but a must not greater than b. Okay, so in this question a is not greater than b, so it may be the causal system. Okay, and second condition is satisfied that ROC is exterior to the outermost pole, so we can say it's a causal system. Clear? In the third case, h of z is given like this, so we can solve it by partial fraction expansion. Again, h of z equal to 2 upon this one, 1 upon this one, 2 and 1. We can calculate this a and this b by the partial fraction expansion, and you all know about the partial fraction expansion. You can easily solve the constants a and b. So there are 2 poles, first is 3 and second pole is at 0.5. Okay, so we can draw the ROC for this z equal to 3 and z equal to 0.5. This is 0.5, this is unit circle 1 and it's a pole at 3. So ROC must be include the unit circle for the condition of stability. So if system is stable, if this system is stable, then ROC must include the unit circle, and if ROC include the unit circle, then there is only one case in which ROC includes the unit circle, and that case is z less than 3 and z greater than 0.5. ROC greater than 0.5 and ROC less than 3. Then that particular ROC will include the unit circle. Otherwise, there are 2 more cases. First case is ROC can greater than 3. If ROC is greater than 3, then it is not including this particular unit circle. Okay, and if ROC is less than 0.5, then also the ROC is not including the unit circle. So there is only one case in which ROC includes the unit circle, that is ROC greater than 0.5 and ROC less than this 3. So for greater than 0.5, the signal is right sided, and for ROC less than 3, the signal is left sided. Okay, so for left sided signal we should write u minus n minus 1, and for right sided signal we should write u of n. So for this 0.5, this part is right sided and this part is left sided. So right sided part can be written as 0.5 to the power n un, and left sided part 2 is constant, minus is multiplied by 2 because this is the left sided signal, and we have already discussed these right sided and left sided signals in the basic Z transform questions. So minus 2 is multiplied with 3 to the power n, this is 3 to the power n u of minus n minus 1. So finally we are having h of n, that is the discrete time form of that particular question. Okay, and finally the result is h of n is equal to this one for the condition of stability. Okay, and the condition of causality, causal means ROC must be right to the rightmost pole or exterior to the outermost pole. And where is the outermost pole? This is the outermost pole, 3 is the outermost pole. Okay, so ROC must be exterior to this particular 3. Clear? If ROC is greater than 3, then it must be greater than 0.5 also. Then we can have the common region greater than 3. So both the signals, both the parts must be right sided. Then only it can possible that ROC is greater than 3. So for this case, 2 multiplied by 3 to the power n u of n right sided, and 0.5 to the power n u of n, this is also right sided. So for condition of causality, this is the h of n. Now there is a third condition, when system is non-causal. If system is non-causal, then ROC must be inside the innermost pole. Which is the innermost pole? This is 0.5. 0.5 is the innermost pole. So if ROC is inside this circle, then ROC must be inside this outer circle also. So both the parts are left sided parts. So how can we define the discrete time signal h of n? H of n is equal to minus 2, because this is left sided, minus 2 multiplied by 3 to the power n u of minus n minus 1, minus 0.5 to the power n, this is 0.5, 0.5 to the power n u of minus n minus 1. Okay, so now check causality and stability if the difference equation is given. So this is the difference equation, y of n minus y of n minus 1 plus 1 by 4 y n minus 2 is equal to x of n plus 1 by 4 x n minus 1 minus 1 by 8 x n minus 2. Yn minus 1, yn minus 2, xn minus 1, xn minus 2, these all are shifted signals. Okay, yn is shifted by 1, yn is shifted by 2, xn is shifted by 1, and xn is shifted by 2. Okay, so we know that we have discussed this property, that was the shifting property. If x of n having the z transform x of z, then xn minus k will be equal to z to the power minus k x of z. X of z is z transform of x of n, and if the signal is shifted by k points, then this x of z will multiply by z to the power minus k. So yn, the z transform is y of z minus y of z multiplied by z to the power minus 1. Why? Because this yn is shifted by 1 point. So z to the power minus 1 plus 1 by 4. This signal is shifted by minus 2. So there will be z to the power minus 2. Y of z equal to x of z plus 1 by 4. This xz inverse, because xn is shifting by 1 point, z inverse x of z minus 1 by 8 z to the power minus 2 x of z. Okay. So we can solve this particular expression like this: y of z 1 minus z inverse plus 1 by 4 z to the power minus 2 x of z, this 1 plus 1 by 4 z inverse minus this 1 by 8 and z to the power minus 2. So what is h of z? The impulse response is equal to y of z upon x of z. Okay. So h of z equal to 1 plus 1 by 4 z inverse minus 1 by 8 z to the power minus 2 upon 1 minus z inverse plus 1 by 4 z to the power minus 2. Okay. So the transfer function of inverse system means we are having the system h of z, and if we have to calculate the transfer function of inverse system, then what should be the inverse function? 1 upon hz is the inverse function. So just inverse this expression, that is equal to 1 minus z inverse plus 1 by 4 z to the power minus 2 upon 1 plus 1 by 4 z inverse plus 1 by 8 z to the power minus 2. Okay. After further solving this expression, we will have the final result like this. Just simply solve these expressions and we will have the final result: z minus 1 by 2 multiplied by z minus 1 by 2, z minus 1 by 4 multiplied by z plus 1 by 2. So there are two poles, first is 8 1 by 4 and second is 8 minus 1 by 2. Okay, minus 1 by 2. So the numerator and the denominator polynomial, if we consider these two polynomials, then we can see that the order of the numerator is not greater than the order of denominator. These are equal. Okay, these are equal. Okay, and if it is right sided signal, then there are two poles, 1 by 4 minus 1 by 2, that is equal to plus 1 by 2 also. Okay, and ROC, when ROC is greater than this 1 by 2, then it will causal system, and if it is causal system, then it includes the unit circle also, and if it is including the unit circle, then we can say it is a stable system also. Okay. So today we discussed about the inverse Z transform and the condition of stability and causality, some examples of that stability and causality, and when a difference equation is given, then how can we check the stable and causal systems. So thank you so much. In next lectures we will discuss some other topics of signals and systems. Thank you.